Hi, everybody. My name is Brendan Mostek. I'm a senior graduating from the University of Pittsburgh, and I've been working in the Fullerton group for the past 2.5 years, primarily working on COMSOL modeling. So I wanted to share with you today a couple tips and tricks, especially looking just at our top-gated MOSFET model, just to explain sort of how COMSOL works and sort of all the different components that goes into our model. So I'm going to share my screen. I apologize that this is filmed on Zoom and not something nicer. I am a chemical engineer, not a film major. All right, but so this is what our model looks like. This is for a top-gated semiconductor model. This is an ionomer model right now. So that means that our cations are mobile, our anions are immobile, and just sort of a quick breakdown of how this structure works. We have a MOSFET here. Our oxide is actually a polymer electrolyte that contains mobile ions that can move in response to an applied voltage here at the top. When you apply a voltage, it causes an EDL to build up at the top and bottom of this electrolyte, which induces carriers into your semiconductor layer here. This is a silicon dioxide layer, inert, that doesn't have any carriers within it. So this part's basically just to make it more realistic to our current devices and model how the voltage drops through that. So we build these devices in the lab, and this model is really helpful for predicting different trends, like how scaling the thickness of this electrolyte will affect the characteristics, for example. So let's just take a look at sort of everything that goes into this, and I want to just sort of explain all the different parts, and hopefully it'll be helpful. I'll try to have sort of timestamps throughout, but I apologize if that doesn't end up happening. I am graduating tomorrow. So to start off, we have parameters. These parameters, you can think of them basically as the variables at the beginning of any kind of code. If you're familiar with MATLAB, C, Python, anything like that, basically allows us to parameterize different components of this build. So we have the length and height of our electrolyte here. We have the stern layer. I'm going to document that stern layer, which is equal to the ionic radius that we're dealing with. So I mentioned that our electrolyte has different ions in it. This is modeling basically lithium ions that are inside the electrolyte. If we wanted to do something like, say, cesium, we could use a value of 0.2, which is approximately the ionic radius of cesium. This will affect the maximum amount of ions that you can induce into a particular area because of the ways, because larger ions can't pack together physically as closely as smaller ions can. Something else to draw your attention to, all of these are basically just constants: temperature, charge of the cations and anions. We're assuming we're using lithium perchlorate here, so +1, -1. And all of the ions we're just assuming are about the same size. For these DC and DA are our diffusion coefficients for our cations and anions. And you notice that when I type in here, I can adjust this in the bottom too, if that's easier. And that's sort of a theme throughout COMSOL, is you usually have a couple different places that you can work with things. We like to change these for our different models. We tend to use 10⁻⁻16 meters squared per second for our cation diffusivity. I don't know how experimentally accurate that is. We don't tend to care about dynamics with the studies that I've worked on. But you can tune this basically to adjust to whatever experimental diffusivity that you can sort of come up with in the lab. Our anions are set to extremely low value, especially relative to the cations right now, of 10⁻30, which basically means they're frozen. And that's what we want for an ionomer. We want only one of the ions to be able to move, in this case, the cations. We want the anions to be modeled as basically a solid polymer backbone that is able to move throughout this matrix. All the rest of these parameters are pretty straightforward. They're just defining different aspects of the model that we'll sort of get to later. And you can always add one of these. So if I wanted to make one, I could call it test and then give it a value 64 nanometers or something like that. And maybe I want to use that for a new part of the geometry that I'm going to define. You can always just make these, you can delete them super easily. You don't want to clear the entire table because that'll make things not work, but I'll just delete that one line and that deletes what we had there. So pretty straightforward for all of that. Let's move on to the definitions. So there's a couple definitions here that I'm actually going to delete because we don't need them. So I inherited this model and there's like a lot of like old stuff that's still lasting in it. So at the end of this presentation, I'm going to give you the final version of this for you to play around with, hopefully without all of the extra fluff that's in it, like these piecewise functions that don't mean anything. So looking at the variables, variables basically are, I broke something. Oh, we don't need that. Okay. Variables are basically, they take either dependent variable, they derive new variables from things that we're solving for in the model. So in this model, we're solving for the voltage across the entire model. We're solving for the electrons and holes concentrations in our semiconductor area here in the middle. And we're solving for our ion concentration, our cation and anion concentrations in the polymer electrolyte. So those are NC and Na, as you can see, sort of all over the place here. And so we can use those variables to then create these, so those dependent variables we can use to create these variables here, such as rho C, which is basically telling us what the net charge density in our electrolyte is. The other things that we can use here are functions. So we can define functions that'll give us variables. And so if I look at this, this is a plot, or this is a piecewise function that defines how our voltage is being applied. So this is our source drain voltage applied across the semiconductor. And we found that in the models that we make, it tends to be better to ramp up variables such as voltage or things that are going to be changing throughout this duration of the model, because it makes it easier for COMSOL to be able to converge to a solution. So we're ramping up our source drain voltage, and then we're going to ramp up our gate voltage in a similar way. You can add different smoothing to this. In my experience, the smoothing doesn't really change too much. So you can just get rid of that, and then it should clean it up. Sorry, get rid of that, and there we go, no smoothing. And that'll basically round off our corners. Extrapolation is good to have just because that way you don't have to define how long your model's going to go. It'll just keep the same final value until the end of time, until the end of your model, I should say. And then this piecewise function is very simple right now, but you can make it as complicated as you want. As long as you sort of continue your piecewise, it has to be continuous. So I'd have to start at 8 here. We go to 10. And I could just make this some crazy value. I can make this like 12 or something like that, and it'll just jump up and do some kind of weird thing like this. This will automatically crash COMSOL. It won't be able to solve some kind of huge step like this so fast. But this is something you're able to input and it'll try to run it. So I'll delete that again. This is also useful to parameterize. I like to have things like maximum voltage, or have this be a variable I call end time basically. And if I go over here, t end, I can make that 8 seconds. And now I can change the duration of our model very easily just by changing this value instead of having to find it here and finding it in the other places later on. Something else to note is if I make up a parameter, let's call this t end 1 or something like that. It should turn yellow. It probably won't turn yellow here because it doesn't. Yeah, so it'll give me an error here, basically because this is not a defined parameter yet. And other places it'll turn yellow or red depending on what it is. Okay, that's enough about definitions. Let's move on to geometry. So you can see we already have a pre-built geometry right here. Basically, the way this works is it works by basically building blocks together. So we have a rectangle that defines our polymer electrolyte area here. We have little lines to separate our stern layers. So these are vacuum regions where the ions can only pass so far. We're modeling them as spheres with their charge at the very center. So one ion radius away, that charge is not able to go any further. So basically the charge density in this area is going to be 0, even though there's technically an ion could be there, just for the sake of the modeling purposes. So we define those, another rectangle for a semiconductor, and then another rectangle, just called rectangle right now. I'll call it SiO2, which is basically our, that's our silicon dioxide layer. I could do a couple different things. I could go up here to the geometry tab, and I can add new rectangles, or say I want to add a circle. I'm going to add a circle here right in the middle. So I'll give it a radius of 10 nanometers. And I'm going to set I could set either its center or its corner. I'll set its center, and I want it to be centered right in the middle of our electrolyte here. So I'm going to define where that center is going to be, and I'm going to set it at L/2 and height over 2. As long as I can spell height correctly, yeah. And now if I build this, we get a circle right in the middle. And I can change this. I can just add 10, and this should move over to the right. And so you can do a lot of different things with sort of building your geometries here. You can test out new geometries for devices really easily by doing this. And I can even remove areas here. So this circle in the middle isn't really going to do anything right now unless we change the physics associated with it. But if I did something like difference, I could add this area and subtract our circle. And then if I build selected, it'll get rid of it, and we have a hole in our object. So I'm going to delete that because I don't want this in this model. But you can make all sorts of weird geometries like this. Oh, I deleted too much stuff. What did I do? All right, let's just go back until we get rid of the circle. All right, cool. Back to our base geometry. So geometry is pretty straightforward if you've sort of worked with any sort of finite element software before. This is a lot better than ANSYS or anything that I've used before. I like it a lot. It's pretty straightforward. And if you say you don't want to delete this, but you want to disable it, you don't want to use it in your current model, you can also just go over here, hit disable. And now if I build all selected objects, it doesn't show up until I enable it again, which is useful to know. So we'll disable that. And that works for all things. I could disable the difference if I wanted to keep that in there too. Say I also have something useless here, like this extra rectangle. I can also just easily delete that down here as well, or I could duplicate it. In this case, I'll delete it so we don't have extra stuff to confuse you guys. All right, moving on to the materials. So I have a couple different materials defined here. We have our electrolyte material, our silicon dioxide material, and then two different options for our semiconductor material. So quickly explaining, there's a lot of different values that you can plug in here. These were just blank materials. So if you go into materials, you can either add a material from COMSOL's library, or you can add a blank material. These are just blank materials that we just filled in with values. The only ones that matter are the ones that have checks next to them. The different physics that you use will give you different checks that you need. And for these models, we just need relative permittivity for our electrolyte. So all these other values, we could change this to 49, and that's not going to change our model at all. Good to have it somewhere close to something that makes sense to you, but it doesn't matter. Same thing for our silicon dioxide. And then you can see that these two materials are both referring to the same section of geometry. So this section of geometry is called 2. And so only one can be applied. And so right now the MOTE2 material is overriding our WSE2. So if I was to disable this, it would automatically switch to now MOTE2 is being used. You have to define slightly more things for a semiconductor, relative permittivity, band gap, etc. But you can find these just by doing some literature search. It took a little bit more time to find it for MOTE2 because it's a little bit of a weirder material, but that's what we're using in the lab for our ionomers. So it's good to try to get these as accurate as possible to give you as accurate of a model as possible. Moving on to the actual physics, this is sort of the most complicated part to understand, But basically, starting off with just the semiconductor module is solving for the electron and hole concentrations in the semiconductor right here. And so it gives you a couple things. It allows you to apply voltages anywhere on the geometry you want. And it'll only, given the way that we've set it up, it'll only end up solving for electrons and holes in this area. So if I just skip over real quick and I look at our solutions, electrons only show up in this area, holes only show up in this area. So our semiconductor works by doing it by solving. We're able to apply to anything within this geometry, but it's only going to end up solving in this area, and you'll be able to see that soon. The main thing I want to bring your attention to is your thickness here. Doesn't really matter for our simulations. This is a two-dimensional model, and it's not isotropic and isotropic, whichever one means that it doesn't matter. The shape of it doesn't matter in the depth. So this doesn't really matter. We just set it equal to 5 nanometers or semi-height, just so it has a value, but it doesn't matter for this simulation. It also solves, the other thing I want to focus on is the dependent variables here. So solves for electric potential, electron concentration, and hole concentration. One thing, if you're building this model from scratch, is both our semiconductor modules, which solves for electrons and holes, and our coefficient form PDE, which is just a fancy way of saying it's going to solve for our ions and our ions in the electrolyte, will both have to solve for electric potential. And you want to make sure that both of these variables are given the same name. So in this case, they're both called V. V is somewhere hidden in here somewhere. But basically make sure that they both refer to the same value, because if you were to make another module or something, it would call it V2 on its own. Say if I wanted to add an electrostatics module instead of the semiconductor module, just make sure it's always called, it's consistent, it's called the same thing. Cross your different modules that have that as a dependent variable, because it will cause problems. So just looking at sort of briefly what all of these different things mean. Semiconductor modules basically just saying where are we getting our material properties from, just from the material describing this region. Insulation and zero charge are things that just sort of automatically generate based off of, you can see how it's like not applicable or overridden. That's COMSOL understanding. Basically, we don't want any electrons to flow out of our semiconductor this way. And we don't want any charge to pass through this way. We're assuming everything at the boundary is held at zero charge. You can also see equations for any of these things here. They're all pretty straightforward for this kind of stuff. Insulator interface, same kind of thing. It's just saying what's, it's separating our electrons and holes from the rest of our model. The main thing you need to worry about that will cause all of these things to be overridden is our charge conservation and our space charge density. So charge conservation is basically just saying that we're conserving charge, obviously, and this is going to apply to our everything, our top Stern layer, our bottom Stern layer, our entire polymer electrolyte, and our SiO2. So this is a little redundant here on the left, but here for illustration purposes. And the other main thing is space charge density. So this is basically telling you what is the, how do we define the charge that exists in this model? Because basically this model is going to be doing a lot of complicated equations for us, partial differential equations, to using these charge densities to solve for our concentrations. So in our top and bottom Stern layer, we're not allowed to have any charge, as I discussed earlier. So these are set equal to 0, and you can see it's excuse me, very thin. So top and bottom Stern layers both have that, and our space charge density in our polymer, or in our substrate, is also 0 because we don't want anything moving down there. It's different in our polymer electrolyte PEO, though. That's that rho C variable that I told you before. That's basically our net charge from the cations minus our anions times their Coulombic charge. Once we get all that, once we put in all of these things, these are all what are called like area, domains. You can come up with different domains depending on the physics that you want. You can add optical transitions and things, but for this model, these are the only things that you need to care about. And then there are also boundaries that we can add here. So the boundaries that we care about adding for this model are metal contact source, drain, and electric potential to the top gate. We use metal contacts for our contact with our semiconductor. We can't use them on top of the electrolyte because the electrolyte is not a metal. COMSOL knows that. But basically, these are both ways of applying voltage to the model. So we have these sort of regions off to the side here in the model that makes it easier to apply these metal contacts. Source is always held at 0. Drain refers back to our voltage that we defined earlier in VD. And this, just to make sure you understand, this VD is not referring to the name of our piecewise function, but it's referring to the name of the variable that refers back to that piecewise function. So our variable is called VD. It's referring to piecewise 4, which is this. This is its function name. So I could change this to VD. That's still not going to affect the rest of this, but I'm going to delete that because it looks really ugly. Going back, so drain does that, and then our electric potential top gate does something very similar. Make sure that you apply this to the correct boundary. We're not applying this to the stern layer. We're applying this to the very top of the geometry. One common problem I had for a while was applying it to the wrong boundary because I wasn't paying attention. And this does the same kind of thing, has an electric potential, and use a contact work function that is appropriate for the metal contacts that you'd be using in the lab. We usually deposit gold, so this is somewhere around the contact work function for gold. So that's the semiconductor module. This has to be coupled, though, with our coefficient form PDE, which is basically a shortcut that we found in order to apply the modified Nernst-Planck equation, which describes how the ions move in response to the applied electric field from the top gate, and then also from all the induced charges occurring because of the source drain voltage going through the semiconductor. So this is just an equation. Read our papers if you want to care about what that equation looks like. But basically, we're solving for our concentration of cations and anions, Nc and Na. And we're basically taking the complicated equation, modified Nernst-Planck equation that wasn't automatically in COMSOL, and we are filling in to a preset partial differential equation template, basically. So you can see all these different terms, and we're basically just defining all these terms, whatever we care about. Most of them are going to go to 0. We don't care about what this alpha term or this A term is. We don't care about what this F term is. We don't care about what this E term is. But we do care about what the C term is, which goes right here. So we're setting those as DC, DI, DA, isotropic, as I tried to explain earlier. And same as before, you don't really need to understand this math super well, but it's all based on the modified Nernst-Planck equation. And these are all referring back to different variables that we defined earlier. Aside from that, this is all pretty straightforward. You don't really need to worry too much about plugging anything in here. Just make sure that you put in initial values for your NC and Na, which are based off of the ion concentration that we are starting with. These are parameterized, I believe. So last thing, if you've ever worked with finite element models before, you know that mesh is extremely important. And so I have 3 different meshes here to sort of explain the process here. Hopefully this loads. Okay, this might take a really long time, so I'm not going to try to generate it. But basically, there's 3 different types of mesh I have. There is sort of the auto-generated one, which hopefully I can build pretty quickly. So the COMSOL will automatically generate a mesh based off of your geometry, and it's usually pretty decent. This one, it shows a triangular mesh for our geometry. And to make it solve, we ended up adding some boundary layers here. So if you go into your mesh node, you can add all sorts of things. You can add, you can make it different shapes. You can add boundary layers. We ended up adding boundary layers because we wanted higher density here at the interfaces where things actually happen. And we don't really care quite as much about the density in the middle because basically no ions are going to build up over here based off of our knowledge of how EDLs work. Our electronic double layer is only going to build up at the top and bottom. Don't care about ions in the middle, basically. So we have much higher resolution down here. And basically what this is COMSOL is going to be doing math at each one of these nodes. So every individual point that you see here is connected to each other, is going to have that complicated math operation done to it to give us our ion concentrations at each of these nodes. And then it'll be able to extrapolate between those nodes to give us values. So general rule of thumb, more nodes, the better, especially more nodes in places that you care about, the better. So you can see our mesh is extremely dense in our semiconductor region because we're trying to model our electrons and holes here. We want very high density here. Our ions are bigger and slightly less dense than our electrons and holes, so we can spread them out using a wider mesh. But based off of finite element theory, it's not good to have shapes that are very different in dimension, I guess I should say. So these long, skinny rectangles here are not very good. Also, squares tend to be better just in general for finite element because it gives you more nodes per single element, single shape to work with. So I have a triangular mesh here, works decently well, but not very optimized. I also have a square mesh, which I'm not even going to try to show you. A problem with our square mesh is to get the same kind of density here at the interface, we have to have an extremely fine, dense grid of materials. It's not like these triangles that are allowed to sort of conform to one another. So for this mesh, it has maybe 50,000 nodes. Our square mesh has over 1 million nodes. So it would take way longer to solve and doesn't even give us a good value. You can change sort of different parameters here, but for our semiconductor modules, we've found that square meshes are just not worth it. But you can still improve upon your typical triangular mesh, and that's by using this sort of optimized mesh. That basically just removes those boundary layers that I was talking about that are poorly conditioned for finite element and replaces them with just finer triangles. And using this, we were able to solve this in a much faster and get more consistent results using a mesh similar to this. You can still play around with this and optimize it on your own. The bulk of your finite element modeling comes down to refining your mesh and sort of troubleshooting to try to make this as good as possible. But for this model, this tends to work pretty well. So going into our study, I can then select that mesh that I just chose right here. So I'm choosing optimized mesh. Don't want to use these other ones. I like the optimized one. I can also change the output times. So I'm going to remember I changed that variable earlier to a parameter called t-end. So let's be consistent about how the model solves this. Basically, I'm going to start at time 0, go up by 0.01 seconds every iteration, solve for it at every 0.01 seconds, and then go up to 8 seconds. It's good to have fairly high resolution of your time intervals here. So we're solving this basically 801 times. If we had made this 0.1 seconds, it would make it a lot harder for COMSOL to solve because things would change a lot more in those intervals. It makes it, the larger the change, the worse it is, the harder it is to basically solve the Jacobian and solve the matrix that defines this entire system. You can also look at our studies and we choose the different physics that we're solving for. So we're solving for the two that we just defined here. And then you can add some other stuff later. But when we run this, you can see it. This current model runs in about 3.5 hours. That's pretty long as finite element models go. But for a complicated model like this, that's sort of coupling our electrons and our ions moving together, it takes a decent amount of time. And this is just on a typical Windows desktop. I believe it's got 4 cores, so it's nothing special. If you have access to cluster computing software, there's ways to optimize it and make it faster and send it to multiple cores. Another interesting thing about this particular model is we have a second study, which is confusingly called study 3. This study only runs in about 3 seconds, which is really nice because this is a stationary study. Doesn't solve for any of the physics. And basically what this is here to do is to help with our post-processing. So I'm going to briefly explain our post-processing system here. Basically, we want to be, when we solve for the values here, like for instance, the ion concentration in our electrolyte, we want to be able to, it'll give us the concentration of our ions in terms of per meter cubed, which is great, but that's not really useful for comparing to literature. We would like per centimeter squared to compare for sheet carrier densities and sheet ion densities. So to do that, we basically have to reduce our units basically by 1. We can do that by integrating, right? So if we take per meter cubed, we integrate that, we can get per meter squared. So to do that, we have to run this extra study, basically to do that within COMSOL instead of exporting to something like MATLAB, which has its own issues we found. So basically by adding this extra study, coming down here, we can define a series of cut lines, basically, along with a parameter name I'm going to call sweep. And so basically this sets 100 cut lines from 0 to 50, which is the length of our polymer. And we can then go into these parametrized curves. And if we plot them, this is going to basically give us a line going along our sweep for a certain amount of height. So sweep basically defined the x coordinates. So every 0.05 nanometers from 0 to 50. And then this allows us to say how long we want those cut lines to be, basically. So it's only showing you the last one here in red, but there's actually 100 of these cut lines that all go from our stern layer up to about halfway, or up to exactly halfway through. So we can integrate our net ion densities. We have the same thing for our semiconductor. Our semiconductor goes the entire length of our semiconductor cut line goes the entire length of the semiconductor, because we're not doing a net of anything here. We want to count up all the electrons in all the holes here. If we did the entire length of the polymer here, then since we build up anions at the top when we apply a positive voltage and cations at the bottom, we'd end up integrating and getting 0 because we'd be solving for a net density that sums to 0. Don't know if that made any sense. Hopefully it does. I'm sorry, it's a little late. But basically, once we do all of this, and we can define other different things in here, like cut points and things that make data analysis useful. And I'll explain that in a second on a different model real quick. But once we do all that, we can go into our derived values and do our actual integrations. So if I evaluate this, we're going to integrate along our cut lines. So our parametrized curve that I just defined in data sets. So I've labeled this. It's taking its data from the last study, which was study 3, which solved for that sweep value. That study also took all of its values from the solution of the previous study, which, sorry, I didn't mention that before. But basically, this is just passing on all the data and adding in this new auxiliary sweep. Theoretically, I guess you could probably do this all in one step, but that's not how we've done it before. So feel free to try to improve this method. Excuse me. But once we evaluate this, this will give us, actually I'll evaluate as I talk. This will give us a list of all of our ion concentrations integrated for each of those cut lines. And so if we wanted more cut lines, we could go back into that sweep variable. We could make it from 0 to 50 in 0.2 nanometer intervals instead of 0.5 or something like that. And it would give us more cut lines. We found that 100 cut lines is more than enough to see the sort of trends that we care about here. And so this usually takes a couple seconds to do this whole integration. But when it finishes, I'll be able to show you sort of the data output that we get here. In the meantime, I will briefly show you this other model that we've been working on. This is an electrostatics model. So it's not solving for semiconductor values. It's just solving for ion movement, basically, in a response to applied field. You can imagine this is basically just the PEO section of the model I was just showing you. I'll also include this if you're part of the University of Pittsburgh and have access to this presentation. You should have access to these different models to look at. And basically, this is a good way to experiment with the data visualization that you can do. So you can do all of this. You can do the same kind of integration that I've been doing before. You can also make plots. So these are plots of different cut points. So I just made I'm focusing just on this point here at the middle bottom stern layer. And I'm using that to plot the ion concentrations at the top point, at a cut point at the top, cut point at the bottom, and then tracking along with applied voltage. And you can see how this changes with time. If we go back to our other model, you can also see things like electron concentration, hole concentration at any time. Say I want to see it at steady state, go all the way down, all the way down to steady state, plot that, and you can see what our final hole concentration looks like. You can also see that in this integration, it's now given me a table. If I want to visualize what this table looks like, I can click this little guy right here, and it'll show us how our ion concentration looks along our sweep. We can do this for electrons and holes as well. And then if I want to export this data, I can go into export, and I can export a table. Say I'm exporting table 1, give it a file name, you browse, you add it, and then you can just export it, and now you have that as a CSV file. That's basically all I needed, all I wanted to talk about. I would encourage you to play around with this model or play around with this other model I have here, especially for the data visualization. The results section is pretty straightforward, so I'm not going to get into it too deep. But a brief explanation is basically for any of these data set or for any of these things, I can add a line graph, I can add a point graph. I can make different sections. So I have an ion section here and a voltage section that'll plot all 3 of these at the same time. And you can choose your data sets here, choose a specific time. And it allows you to very quickly visualize all this data without having to export it. You can also change the titles of things. I wrote the title for this. Instead of whatever COMSOL automatically generated, you can add legends and stuff. So I will be providing this to the Fullerton group. If you're not in the Fullerton group and watching this, get in touch with them. I'm sure they'd be happy to send it to you. But I know that this presentation's already been too long. So I hope that this has been a decent tutorial explanation of how everything works. I will stop sharing. I appreciate you coming along for this ride. If you have any questions, feel free to reach out to the Fullerton group, Dr. Susan Fullerton at the University of Pittsburgh, and I'm sure that she'd be happy to send me your way. or Shubha Mawate, who has been sort of my mentor throughout this entire process. I'm sure he'd be able to help answer any of your questions. So I appreciate your time, and I hope you have a good day.